Hello, welcome to this video on stiffness of common structural elements. In this video we shall see the expressions of different stiffnesses, then the stiffness elements in series and parallel, and the application of the stiffness concept in real field problems. The definition of stiffness goes like this. Stiffness is the force required to produce unit deformation. Generally we express stiffness by the symbol K, so K equal to force divided by deformation. So it symbolically we can write K equal to F by delta, where F is the force and delta is any displacement or deformation. So this case that we have taken, K equal to F by delta, is a generalized case which includes all kinds of forces and all kinds of displacements. If we go to specific, then it can be linear displacement, when we can write K delta equal to F by delta. A rotation, K theta equal to M by theta, moment divided by rotation. And for torsion it is K phi, we can write equal to torsional moment T divided by angle of twist phi. Similarly, for shear deformation, we can write K is equal to shear force divided by shear deformation. Now let us see the stiffness of very simple element, the axially loaded element. So here we have considered a column of length L and cross-sectional area capital A. It is subjected to an axial force of P at the top. So due to this force, the column will compress in length, so it becomes like this. So it compresses by the distance, say delta L, elementary small distance delta L. Now how do you express the relationship between P delta L and L? This is given like this: delta L equal to PL divided by AE. A is the sectional area of the column and E is the modulus of elasticity of the material of the column. So rearranging this, we can write P by delta L, that is force divided by the deformation, equal to A by L, and this is nothing but the stiffness. So axial stiffness we can write as AE divided by L. Now let us consider a beam element which is fixed at the end B, and an applied moment MA is acting at the other end A, which is hinged. So at the end A, I am able to rotate the beam. So I am rotating this beam, say by an angle of theta A here. In doing so, I require a force or a moment. So that moment is the applied moment MA. We know from mechanics the relationship between this applied moment MA and the theta A at this end is like this: MA applied equal to 4EI by L theta A. So rearranging, we get MA applied by theta equal to 4EI by L, so that is equal to the stiffness against rotation for this beam element. So we can write K bending equal to 4EI by L. Now let us take a beam element which is settled at one end. So both the ends suppose are fixed and one end is settled down by an amount delta here. As a result, some end moment will be generated here, which are say M here and M at the other end also. The moments will be same because there is no external force, that is, we are not considering any gravity load at this point. We know from mechanics the relationship between such moments equal to M equal to 6EI delta y L square, where L is the length of the beam, E is the modulus of elasticity, I is the moment of inertia of the cross section of the beam, and delta is the differential displacement between the two supports. So rearranging M by delta, the force divided by deformation, is the stiffness given by this. So we can write K for displacement of one end of a beam is equal to 6EI by L square. Now we take another case, the stiffness of column against lateral sway. So a column was standing vertically here like this, shown by the dotted line, and because of the application of a force P at the top of the column is swayed by an amount delta at the top. So this will produce a moment similar to that of the case we have discussed in the last slide of the beam having differential displacement at the ends. So it will generate a moment m here and similar moment at the other end m. We are neglecting any other span load in between. So we have already seen the moment relationship is given by m equal to 6ci delta by L square. Now what we do, we take moment of all the forces in this system about the base, about this point. So one force is P and this lever arm is L, another force is M, another force is M at the bottom. So the equation becomes PL equal to M plus M or equal to twice M. Now in this differential displacement analogous to the beam element, the M moment is equal to the 6ci delta by L square as we have seen in the previous slide. So we can write PL equal to 2 into this 6ci delta by L square. Now we rearrange this P by delta, which is the force per unit deformation, which is the stiffness, is 12 VI by L cube. So for column sway, the stiffness is equal to 12 VI by L cube. Very important formulation for vibration analysis of the buildings. Now let us take the case of torsion. So torsion in a system can be applied in two ways. Keeping, say, for the first figure, keeping this end fixed, left end fixed, we give a twist in the anticlockwise direction for this end. This is the vectorial notation of the anticlockwise moment. You see now, this is a computer model actually. The lines which were straight in the beginning are now curved. These longitudinal lines are now curved, having a twisting angle which has been applied at the free end. The other end is fixed. Torsion can also be applied by other way by giving some opposite moments at the two ends of the system. So here we have given anticlockwise moment at the right end of this pipe and a clockwise moment at the near end, and this will produce a torsion in the system. So this is the now relationship between torsional moment T and the angle of the twist phi is given by this G phi IP by L. L is the length of the system, G is the modulus of rigidity, IP is the polar moment of inertia of the cross section of the system, and L is the length of the system. So this gives the relationship between the torsional moment and the angle of twist. So rearranging this force by displacement T by phi equal to G IP by L. So this is the stiffness for a system in torsion, G phi IP by L. Now let us see when the springs are in series and parallel. This is a very important concept because all these systems, real systems, will be combined out of many stiffness elements. So some will be in series, some will be in parallel, some will be in combination of various complexities. How to get the resultant stiffness out of all this complex system? So we are considering simple two cases. One, the springs are in series here. The spring K1 having stiffness K1 and the next spring having stiffness K2 are in series. In this figure again K1, K2, K3 all are in series one after another. So these are springs in series example. You can also have springs in parallel. So here in the left hand side figure you can see one spring is having stiffness K1, another spring is having stiffness K2, and they are subjected to some deformation by some load or some force, and they will act together to resist that force. So they are in parallel. Here three springs are shown in parallel. So these are the springs in series in parallel in physical realm. Now how to get their combined stiffness? So first let us consider springs in parallel. So these are the two springs which are parallel to each other. One is having stiffness K1, another having stiffness K2. They can form an equivalent spring of a bigger stiffness or a combined stiffness, which will be called as equivalent stiffness, K equivalent. And this resultant spring, hypothetical spring, will be undergoing some displacement which is equal to delta equivalent or equivalent displacement. We can very easily understand that if the primary system undergoes a deformation by certain amount, then the equivalent spring also will undergo by this same deformation downward, and the force in the two springs, original springs are say F1 and F2. Force experienced by the equivalent spring is equal to F equivalent as shown in the diagram. So we have here K1 is the stiffness of the first spring, K2 stiffness of the second spring, K equivalent stiffness of the equivalent spring. Now if we consider the forces, the equivalent force F equivalent is equal to F1 plus F2, because whatever force you apply here will be shared by the two springs in some proportion. So this is equation 1, and since force equal to stiffness into displacement, so we can write F equivalent equal to K equivalent into delta equivalent. Delta equivalent is the equivalent deformation of the resultant spring or equivalent spring, and F1 equal to K1 delta 1, F2 equal to K2 delta 2. So out of this we get this second equation. But you see here delta 1, delta 2 and delta equivalent are all same, because this is a rigid body. So if it is going down by 1 centimeter, both the spring will go down by 1 centimeter, and the resultant system also will go down by 1 centimeter. So the deformation of the first spring, second spring and equivalent spring all are equal. So if we set this relationship in equation 2, we get K equivalent equal to K1 plus K2. So this is very simple relationship for springs in parallel. It is the summation of spring constants of the individual elements. Now we are taking the second case when the springs in series. So we have considered two springs here. K1 is this first spring and K2 the stiffness of the second spring. They undergo displacement delta 1 and delta 2 respectively, and the resultant displacement we are writing by delta equivalent. There will be also a force in the first spring, say F1, and second spring F2, which are related by this equation 1, F equivalent equal to F1 plus equal to F2. Why it is so? Because through this spring, if we apply any force, it will be experienced by the two springs of the same magnitude. So if you apply a force at the end of the spring system, both the springs will experience the same force. That's why we are writing F equivalent equal to F1 plus F equivalent equal to F1 equal to F2 as given in equation 1. Now the equivalent displacement is equal to delta 1 plus delta 2. Why? Because if you move the spring by certain amount, whatever displacement which it is suffering will be shared by the two springs. If this moves by 1 centimeter, this moves by 2 centimeter, the resultant displacement will be 3 centimeter, because they are in series. So we are writing delta equivalent equal to delta 1 plus delta 2. This is the equation number 2. So delta equivalent equal to force by stiffness. So we are writing F equivalent by K equivalent. Similarly, delta 1 equal to force F1 divided by K1, and delta 2 equal to force F2 by K2. This equation, now we substitute the equation 1, that is all the forces are equal. So if they are equal at the numerator, they will be cancelled, and we are left with the expression 1 by K equivalent equal to 1 by K1 plus 1 by K2. Here we have taken two springs in series. There will be cases when there will be more springs, and then we can have a generalized expression like this: 1 by K equivalent equal to summation 1 by Ki of any I stiffness. Now we have considered basic two cases, spring in series and spring in parallel. But in real field there will be combination of these two in different patterns. So let us see how to tackle those cases. In the first figure we have taken two springs in series. Along with that there is another spring in this slide. We are looking at finding some equivalent spring constant for complex systems which are consisting of springs in series and springs in parallel. In the first figure here we have two springs in parallel first, and then along with that we have a spring in series here at the bottom. So we'll first apply the expression for parallel spring. So we get K equivalent 1 equal to summation of the two spring constants K plus K. And now we have one spring constant K equivalent at the top and another spring constant K at the bottom, which both are in series. So series formula will hold good, and you get 1 by K equivalent equal 1 by K equivalent 1 plus 1 by K. Now let us go to this second figure here. Here at the top we have two springs having constants K1 and K2, and at the bottom we have another two springs having constants K3 and K4. So these two are in parallel condition, and K3 and K4 are in parallel also. So we first find out the parallel combination of these two, K1, K2. So K equivalent 1 equal to K1 plus K2, and similarly K equivalent 2 equal to K3 plus K4. Now this K equivalent 1 is at the top and K equivalent 2 is at the bottom, which will be in series. So final combined expression is given by 1 by K equivalent equal to 1 by K equivalent 1 plus 1 by K equivalent 2. This is all right. Now if we take a portal frame, the situation is slightly different. Understanding is required, because earlier we had used springs which were hanging with a load at the bottom. So whether it was series or parallel, etc., was very clear. Now in the portal frame we are applying a lateral load at the top, and it is swaying towards right. So here it is not that springs are hanging and load is there downward, not like that. So whether they are in series and parallel, that is a question. The answer to this is, we have two springs here. One spring is the first column, another spring is the second column. Their stiffnesses are guided by their length L1 and the moment of inertia I1 and L2 and I2 for the second column. So the columns are having stiffnesses say K1 and K2. Now whether this K1 and K2 are in series or parallel can be understood by noting that in parallel series of springs, the springs undergo same deformation. So here the first column is moved by certain amount here. The same amount is the also movement for the second column. So these two springs, two columns have moved by same amount at the top, so they are in parallel. The stiffness of the left hand column can be given by this expression K1 equal to 12 EI1 divided by L1 cube. Similarly, the stiffness for the second column is given by K2 equal to 12 EI2 divided by L2 cube. So since these two are in parallel, the equivalent spring constant is given by K equivalent to K1 plus K2. Fine, now let us take a two-story portal frame. What happens now? We are now in a position to say that this K3 and K4 are parallel and K1 and K2 also parallel. So first let us find out the parallel equivalent of the springs. So at the bottom story you have K equivalent 1 equal to K1 plus K2, and at the top story you have K equivalent 2 equal to K3 plus K4. So you have a spring here, another spring here. So now these two are in series, because the displacement suffered by this spring, say this much, and displacement suffered by the top spring will be higher at the top. So they are not same, so these springs are in series. So we'll apply the series formula, and the final spring constant is given by 1 by K equivalent equal to 1 by K equivalent 1 plus 1 by K equivalent 2. From the relationship you can find out the reciprocal, and you can calculate the value of K equivalent exactly from the numerical values of these two. Thank you very much for watching the video. Please subscribe the channel, like and share the videos, put your comments, put your queries, technical queries. I'll be glad to answer those. Thank you very much, and see you again in the next video.